Alright, for our final exercise, we're going to look at concentrations in air, the compartment of air. The concentration expressions we're going to look at are mass per volume, volume per volume, mole per mole, and I'll comment on a few others as well in terms of how these are all related. Reading across the table here in terms of units, for looking at mass per volume, we typically see units reported in something like micrograms per meter cubed. When we're dealing with volume per volume, we'll see units of parts per million by volume, parts per billion by volume, mole per mole is mole fraction. So a really key piece here in looking at concentrations in air is the ideal gas law, which I'm sure everyone remembers from general chemistry, PV equals nRT, all kinds of ways to manipulate the ideal gas law so that we can get relationships between moles and volume, or volume and moles, or we could move pressure around. That'll come into play later. So let's look at a common conversion that one is going to want to do, and that's going back and forth between mass per volume and volume per volume. And so specifically with respect to mass per volume, we'll look at units of micrograms per meter cubed, and we're going to want to convert that to, say, parts per million volume or parts per billion volume. What we're trying to do here is move from, as we've seen, mass per volume, and we can think of it in a couple steps. Mass per volume first to moles per volume. That's a pretty easy conversion, making use of molecular weight. Then, going from moles per volume to volume per volume, we can make use of the ideal gas law. It also turns out that we can approach volume per volume from other directions, such as mole per mole ratio can get us to volume per volume. Pressure, partial pressure to pressure total, can also get us to volume per volume. Both of those make use of the ideal gas law. I'll give you some questions later to practice that. Right now I want to focus on this pathway of mass per volume, ultimately getting to volume per volume. So here's our example problem. The concentration of SO2 in air is 260 micrograms per meter cubed. What is the concentration in units of parts per billion by volume? Assume temperature is 28 degrees C and pressure is 1 atm. So one thing is, often when we do a concentration calculation in water or concentration calculation in soil, temperature and pressure are less important. Temperature can impact concentrations and reactions. Rarely do we worry about pressure in water or soil. So that's important, whereas in making calculations in air or in gas, knowing both temperature and pressure are critical. Alright, so first let's convert our mass per volume to a mole per volume, and that's pretty easy. 260 micrograms of SO2 per meter cubed. Take the molecular weight of SO2, micrograms per micromoles, do a unit conversion here to get from micromoles to moles, and we get about 4 times 10 to the minus 6 moles per meter cubed. Now we'll make use of the ideal gas law. So we can do some rearranging and solve for volume, since we're ultimately wanting to get to a volume ratio. So the volume of SO2 is equal to moles of SO2 times RT over P, ideal gas constant R, temperature T, pressure P. We can multiply both sides of this expression by 1 over V total. When we do that, we have volume of SO2 over volume of total. That's where we were trying to get to. And we also get the moles of SO2 over volume total, which is something that we know. We have that, we calculate that in the previous line. So we take our answer that we determined just 2 lines above, our moles of SO2 per meters cubed, and we're going to then apply RT over P. There are many different R's we can use that have different units associated with them. I used one that makes the most sense for our problem, which is 8.205 times 10 to the minus 5 meters cubed atm per mole K. Here's temperature. Remember that you need to work on the thermodynamic temperature scale, so that would be 28 degrees C plus 273, so that you're in Kelvin units. 1 atm, you do the calculation, and it's 1 times 10 to the minus 7 meters cubed of SO2 per meters cubed of air. I'll come back to this comment in a moment. So, our definitions. This is similar definitions as when we're working parts per million mass, parts per million volume. So parts per million mass, parts per billion mass, we saw earlier on with soils. Parts per million volume, volume of the chemical we're interested over volume total times 10 to the 6 to do our conversion of expressing it as 1 part per million. part per billion, volume of chemical per volume total, multiplying by 10 to 9 to do our conversion of 1 in a billion. So we take our answer from above, which is a volume ratio, meters cubed SO2 per meters cubed air. We multiply by 10 to the 6, and we get 0.1 parts per million by volume. Take that same answer and multiply it by 10 to the 9, and we get 100 parts per billion by volume. Just two different ways to express the same thing. And just to circle back up here, we could take this answer, multiply it by 100, and express it as a percent, and it would be a very small number. And so typically we choose a unit so that we're working with a whole number. You know, in this case, probably would make the most sense to talk about it as parts per billion volume. However, if we were comparing it against something like CO2, which we often think about in terms of parts per million levels, or if we were thinking about it relative to the amount of nitrogen or oxygen in the atmosphere, which we express as percent levels, that could influence the units that we choose. Okay, thank you very much.